1.4 is on solving systems of linear equations. So let's go over that. I'm sure you've seen much of this before, but let's start from the beginning. So suppose, well, not like the beginning, but just, farther along than we have in the past. So you have a linear means you have something like this: ax plus by equal to c, where of course x and y are your variables, a, b, and c are constants. Not all zero, I guess, is what we want, but basically we know that's a line. So two variables, you're looking for ordered pairs x, y that satisfy the equation, and you get a line. Also linear would be something like, wait, that's not what I want to do. Would be something like this. If you had ax plus by plus cz equal to d, that actually could have used lowercase to be consistent. Sorry, d. This has three variables, and this represents a plane. Again, if you had seen this in Calc 3, you would have, anywhere along the way, you would have seen something like that. So that's a plane. The key to all of that being linear is what? The key is the numbers on the exponents are 1 of the variables, right? The variables exponents are 1. That's what makes it linear. So the linear aspect is just that. So in 2 dimensions, let's do a graph over here. Don't want to use that color. So in 2 dimensions, you have lines. And then you have, what we're going to look at are the systems of those equations. So when you have lines, you may have a line like this. Call that like L1. Then you could have basically 3 different cases. First case is the simple case. You have a line L1, and let's just say L2, like that. And you have basically the concept is, as I would explain in an algebra class, every point on the line satisfies equation 1, and it's an ordered pair x, y. Every point on this line, which are all of these points, satisfy equation 2. Is there a point that satisfies both? And if you graph it, you get that intersection, all of which we know and is familiar. So that intersection point right there, x, y, we would say is the solution to the system. You have, so that's basically case 1. Case 2 is you'd have like parallel lines. Okay. Duplicate that nicely these days, like that. So those lines would be parallel. And so there are no, so we'll call it like L3. There are no solutions that satisfy both. And the third possibility is basically you end up with like the same, let's do it like this, let's duplicate. You end up with the same line. Can't really do that. So let's just change the color on that. So, so something like that. You end up with the same line, and then you have one on top of each other like that. Okay, so usually I just draw it like a thicker line or something, right? So that's the third possibility. And so this is where it starts. This is where this description and how we're going to define things start. So your system might look like this. 3x, this is just an example, plus y equal to 1. 6x plus 2y equal to 2. And so you have, different lines, line 1, line 2. I didn't graph, I don't think I graphed those to scale. I'm just showing you the idea. What we're going to do, just a little kind of precursor concept, we're going to make these into matrices. We're going to put in 3, 1, 6, 2. We're going to put in the coefficients. The constants, sorry. The coefficients are the left-hand side there. And then the constants, like that. And then we'll solve the system. So we're gonna make this a 0 down here and solve. So that's where we're heading. But we'll do a couple things before that. So here's a definition. I'm going to call it a definition. It's just, I'm not sure why I labeled it like that. This is really just, we have 3 outcomes. For what we call a system of 2 equations actually, this is for invariables. That's the idea. So 3 outcomes for a system of, sorry about this, for invariables. I'm trying to do it more in general now. We have either these possibilities, and we'll get more into this as we go. But the possibilities are 1 solution, infinite number of solutions, that'd be case 3 up there, so infinite number of solutions, and 3, no solution. We call, if you have 1 solution, if you have a solution, we say this system is consistent. So we say system, or the system is consistent. And so these 2 cases, 1 solution or infinite, we still say it's consistent. So those are consistent, and this would be inconsistent. Oh, sorry, that I wrote it the wrong spot. Those are consistent, and then this is inconsistent. Okay. We say 2 systems are equivalent if they have the same solutions. So 2 systems are equivalent if they have the same solutions. So when you're solving systems, and I don't even think I have a prepared 2x2 ready to go. We'll go right to a 3x3. So each of these, so when we solve systems, each of these operations, so each of these operations yield or give us, we say yields equivalent systems. Sometimes I'll use just like a squiggly to say like one system's equivalent to the next, or one matrix equivalent to the next. They're not the same, but they're equivalent solutions, is how we say that. And so if you have a system, so there's my system up there. That's what I was going to use. 3, 6. Oh, so yeah, if you interchange equations, so 1, so let's consider this system right here, and then if you interchange it, that doesn't doesn't affect the solutions, right? So you can interchange two equations. So interchange two equations. So for example, you just end up with 6x plus 2y equal to 2. 3x plus y equal to 1. Same solutions as the original, right? It's the one above there. Let's just star that. Keep track of which one we're talking about up there. And then 2, multiply an equation by a non-zero constant. So basically multiply an equation by a non-zero constant. So, and it has to be, it's like, that's basically multiplying both sides. So multiply on both sides of the equation. That's balancing the equation. Done that before. So for example, if you multiply, this is the notation we'll start using. So if I do like 1/2 equation 1, so let's call this equation 1 here, and I multiply by 1/2, then what I get? I get 3x plus y equal to 1, and then 3x plus 1 equal to 1. So, those are the same, sorry. Poor choice of examples, I suppose. I was using that for something else, so let's change this one a little bit, so we don't get zeroed, so we don't zero stuff out. Let's make that a 4. So if you do that, you get, okay, so interchanging. So this example was meant to show you get the same thing previously. I'm going to go ahead and change that because it was just a 2x2 system of an example, so I'll put a 4 there. And now they're going to be different equations. And so now I get 3x plus 2y equal to 1 on the top. And then this is just the 3x plus y equal to 1. So for that system that we're talking about in question here, it does not change the solution. That's the whole point to what I'm writing now. Next is this one, add a multiple of an equation to another equation. So by doing that, we add a multiple, and then that's basically how you start solving the system, if you recall. So I could come in here and multiply by, say, -4 and add it, and that'll eliminate something. So you could do something like this, maybe. I'll just show you now. I wasn't going to yet, but let's do it. Well, first of all, here, there's still that 2 there. So let's get rid of that 2. Let's suppose you did that first. And let's suppose you have this system now. And so now let's eliminate the y. This is where we're heading. So if I did, here's equation 1, not touching that. But now, what if I did -2 times equation 2 and add to equation 1? So if I do that, I get -6 plus 3 is -3. And then yeah, those are the same. No, I'm sorry. That's fine. Yes, -3. And then negative 2 equation. So then the y is gone. You get negative 2y and 2y is gone. And so the y is gone. And then you do the same thing to the constants and you get a negative 1. So you end up solving and get like 1/3. And then you could find your y. Okay, well, that's where we're heading, right? That's what we want to go to. But keep track of just, our goal is not to just solve systems, right? Our goal is to figure out the theory behind all this stuff and how to apply matrices. So keep in mind these 3 different things and how we're going to convert that to more of a general concept. That's what we want to do. Okay, so next, let's see where we're at. The next thing is really where we're heading. It's called row echelon form, back substitution, Gaussian elimination, and Gauss-Jordan elimination. So we will do that next. And go there soon. I'm going to go ahead and stop, do a short video at first because the next one will be kind of long, which I do not want to stop in the middle of because there's a bit to go through there. Yeah, I'm checking out my notes there. And if you end up downloading the notes, excuse me, you can follow along. I do change sometimes a little bit. You may notice as I go. Sometimes there might be little mistakes here and there. Usually nothing real big, but I might clarify things in these notes. So look at both. This is by no means a everything perfect sort of situation. Just trying to get as many of these as I can done for you, and then we can talk more in our problem sessions.